This call is now being recorded.
All right. So I want to start by a remark. Suppose you have two integers which are coprime. Then last time I said that well, okay, if they are coprime, then last time we showed that K is a generator of integers modulo n. So this means that there is some V such that, in particular, Vk is equal to 1 modulo n. Which means that there is some U such that Vk plus Un is equal to 1. Okay, so and these are called UV are the Bezout coefficients. Which are generally not unique. So just be careful. But this kind of statement has a more general version where you could take any two integers with which are not necessarily coprime, and then the Bezout coefficients will give you that I mean U times n plus V times K would be equal to the GCD of K and n. But we actually only use this version so far. So this is a proof. Now we continue with the classification of finite abelian groups, and I remind you that so we write an abelian group now with an additive notation. And suppose the order of the group is some well, has prime decomposition. We define the set for now GPI, which is all the elements X in G, such that the order of X is some power of Pi. So Pi to the n, X is equal to 0 for some n. Right? And n can be different for different x's in this group. And we showed that this is a subgroup of G. And furthermore, and G is isomorphic to the direct sum of all the GPIs. And these are called primary PI group. Okay, and of course, the order of GPI, it must be a power of P, of PI, because if there would be any other prime that divides the order of GPI, then by Cauchy, you would have an element of this order, and this would contradict the definition of GPI, because GPI has only elements whose order is a power of PI. So the order of GPI is some power of PI, and since we have this isomorphism, we actually get that the order must be PI to the NI. Right? It cannot be otherwise, because then because the isomorphism implies that the two sides have the same order, and the order of the right hand side is the product of all orders. So this is where we left off, and where we're heading. I mean, the classification of finite abelian groups would be to decompose G into a sum of cyclic groups. This is kind of the atomic units that we understand completely. I mean, a cyclic group is always isomorphic, or finite cyclic group is always isomorphic to integers modulo n for some n. And we know all the generators of integers modulo n. We know that every subgroup of integers modulo n is cyclic, and so on. This we understand completely. And now, to get to a decomposition of G into a direct sum of cyclic groups, we need to decompose each of the GPIs. Here it should be 1. Each of the GPIs into a product of cyclic groups. So the GPI, for example, it could be that you have integers modulo 5, direct sum integers modulo 5, but you could also have integers modulo 25, which we showed last time is not isomorphic to integers modulo 5. I mean, integers modulo 5 times itself. So this, for example, for PI equal 5, GPI so okay, but you see that even if this is I mean, in both of these cases, GPI is, well, it might not be cyclic in itself, but it is a direct sum of cyclic groups. And we now go for the main lemma to do this, and this is the following. Let G be finite abelian P group. P group, it means that the order of G is a power of P. And furthermore, let A be an element of maximal order. This means that the order of A is greater or equal to the order of B for any B in G. And the claim of the lemma is that there exists a subgroup K of G such that G is isomorphic to the group generated by the maximal order element, direct sum K. Okay, and the proof of the lemma is rather technical, so I recommend that you follow the notes. I will try to convey the proof here as well, but I mean, in case you miss something, you can always ask now, but you could also follow the notes after the session. It's kind of a bookkeeping, so there's not much to understand rather than just to follow. So consider the set of subgroups H of G such that the intersection of the group generated by A with H is trivial. Trivial, it means that it contains only the neutral element. This set is not empty. I mean, because you can take, for example, H equals the trivial group. And it is finite because G is finite. Hence, it has an element K of maximal size. So K is a subgroup of G with intersection A and K equal to the trivial subgroup, and the order of K is maximal. And we claim will show that G is in fact the sum of these two groups. And when I write this plus, what I mean is you simply take all the sums. So you have an element in the first group is let's say R A, and an element in the second group is some K. So this is R is in Z, and K is in K. You simply take all the sums. Okay, so that's what we want to show. And suppose towards contradiction, that a G is not the sum of these two groups. And let B in G be a non-zero element such that B does not belong to the sum of these two groups. Now, remember, G is a P group. Since G is a P group, the order of all the elements in a P group are some power of P. So there is some integer J such that Ej times B is equal to 0. And there is a smallest L less equal to J such that PL times B is in the group A plus K. So you see, if P to the J times B is equal to 0, then it clearly it belongs to A plus K, because A plus K contains 0. So there is a smallest integer L such that PL times B is in this group. Whereas I remind you, B is not in the group. Then element C equals P to the L minus 1 B is not in the group, in the sum of these two groups, by minimality, by and but PC, which is like P to the L B, is in this group, in the sum of these two groups. So there exists T in Z and K in K such that PC is equal to TA plus K. Since let's say the order of A is P to the N, and since this is maximal, then for each X in G, Pn X is equal to 0, right? But then in particular, let's see. Pn minus 1 times Ta plus K is equal to Pn minus 1 Pc. So this must be equal to 0. This is P to the N times C. And this must be equal to 0. So Pn minus 1 Ta is equal to Pn minus 1 K inverse. But then you see the right-hand side is in K, and the left-hand side is in the group generated by A. And we said that K is, I mean, the intersection of A and K is trivial. So Pn minus 1 Ta must be 0. Okay, now since the order of A is P to the N, and Pn minus 1 Ta is 0, it means that Pn must divide Pn minus 1 T. So I can write T equals P times something. Let's see, P times M. So using this, I can do, I can write PC as, well, PC is like Ta plus K, right? This is here. But T is PM, so I can write it as PM A plus K. And this means I can write K as PC minus PMA, which is simply P times C minus MA. . So now we set D to be equal to C minus MA. So P times D is equal to P times C minus MA, which is equal to K. So PD is an element in K, in capital K. But D is not an element in K, since if D equals C minus MA is in K, then C would be equal to D plus MA, or rather MA plus D, would be in the intersection of A and K, which is trivial. Okay, and C is not a zero element. Well, C by design, C. Sorry, this would mean that C is in the sum of A and K. And by design, C was chosen to be an element, not an element in G, which is not in A plus K, right? This is the assumption that G is, I mean, A plus K is not spanning all the elements in G. Now, the set age which is all the sums of the form X plus ZD, where X is in K and Z is an integer, is a subgroup of G with K contained in H, right? I mean, of course, I can take here the Z to be equal to 0, so I get all of the elements in K. And K is maximal such that the intersection of the group generated by A with K is trivial. So by maximality of K, H intersection the group generated by A must be non-trivial. I mean, we actually need to show that K is not equal to H, but this is easy because D is an element in H, because it is 0 plus 1D, But D by design is not an element. Well, yeah, D by design is not an element in K. Let me. Wait, there is an issue here because I think D. Yeah, we said that D, I mean, we showed that D is not an element in K. So, so K is not equal to H completely. And this means by maximality of K, that H intersection the group generated by A is non-zero or non-trivial. Okay, well, we're approaching the end. So let W be an element in the intersection of H and A, which is non-zero. Then I can write W on one hand equal to SA for some integer S. And on the other hand, it is equal to, say, K1 plus RD. This for some R and S in the integers and K1 in capital K. Now I claim that the GCD of P and R is 1. I mean, if the GCD of P and R was bigger than 1, then since P is prime, I could write R as some I mean as Py for some integer y. Then as PD, which is K, is of course an element in capital K. We would have W, which is non-zero. It's equal to SA on one hand, but it's also equal to K1 plus RD, but R I can write as PY, so PYD. And this really means that it is both an element of the group generated by A, because it is SA, and it is an element in K, because it is K1 plus some integer times I mean, some integer times another element in K. So it is in the intersection, and this cannot happen. And what this means is that the GCD of P and R is 1. So I can find Bezout coefficients for P and R. Pu plus Rv is equal to 1. Then I can write C. C is, of course, 1 times C, which is equal to Pu plus Rv C. And this is equal to UPC plus VRC. Now PC is TA plus K. And RC, well, C is D plus MA. So I get RD plus MA. And RD is SA minus K1, right? I mean, this is R. So I get TA plus K plus V SA minus RD. Oh, SA minus K1 plus RMA. And now the final step, I open everything. So this is UTA. Sorry. I open everything and I take all the elements with the factor of A. I get UT plus VS plus RM A plus UK minus VK1. And what you see here is that C is an element in the group generated by A intersection K. This is a contradiction. We chose C to be not in this group. So this. And we conclude that G is simply equal to A plus K. So G is equal to the sum of two groups whose intersection is trivial. Then we may define simply a map from G into the direct sum by taking an element X into, or I guess it's easier in the other direction, from A plus K into G. I take SA comma K, and I simply send it to SA plus K. And you can check that this is an isomorphism. I mean, generally speaking, if you have two groups that whose sum is the whole group, two subgroups whose sum is the whole group, and their intersection is trivial, it means that the big group G is simply isomorphic to the direct sum. Okay, so this completes this proof. Any questions about this lemma? Okay, so with this, I can formulate the first version of the structure theorem, or classification theorem. And this is as follows. Every finite abelian group G is isomorphic to the direct sum of cyclic groups each of prime power order. And in symbols, it means that G is isomorphic to integers modulo P1 to the S1, direct sum integers modulo let's say PL to the SL, where the P1 up to PL are not necessarily unique primes. Okay? And how do you prove it? It's very easy, using the lemma. We know that G, I mean, let's say without loss of generality, I simply write G equal to GP1 up to GPK, where I have the order of G is P1 to the N1 up to Pk to the Nk. And of course, each GPI is a P group or a PI group. So by the lemma, GPI is isomorphic to a cyclic group, direct sum some subgroup Ki, and of course the element A has to be of order a power of Pi. So repeating this, we get the GPI is isomorphic to integers modulo Pi to, let's say, beta 1, direct sum, integers modulo Pi to the beta say M, with, of course, the sum beta 1 up to beta M, it must be equal to Ni. I mean, since the order of GPI is Pi to the Ni. Okay, and I do it for all the GPIs, and I get the decomposition I want for G. Okay, so this is the first classification theorem, or the first version of the classification theorem. It means a finite abelian group is a sum of cyclic groups of prime power order. Okay, so now as an example, what can you do with this classification? The integer 100 can be written as a product of prime powers in 4 ways. One way, of course, is you take 2 times 2 times 5 times 5. Then the other way is that you take 2 times 2 times 5 squared. Then you can do a 2 squared times 5 times 5. And the last way is to do 2 squared times 5 squared. And by the classification theorem, if G is of size 100, it must be isomorphic to one of the four groups that correspond to this prime decomposition. I mean prime power decomposition. So I have the first one would be integers modulo 2, some integers modulo 2, some integers modulo 5, some integers modulo 5. This is A. The second prime power decomposition would be integers modulo 2, integers modulo 2, integers modulo 25. Then the third one would be integers modulo 4. Integers modulo 5, integers modulo 5. And the last one is integers modulo 4, some integers modulo 25. Okay, and that's it. The classification theorem tells us that this is, I mean, this is all the possibilities to get a group, an abelian group of order 100. So what about integers modulo 100? Why is it not in the list? Anybody?
Wait. So it's already covered, right? It's one of. Wait. Oh well, modulo 100 is not a PI, right?
Is what?
It's not a power of a prime.
Yeah, but the classification theorem tells me that a group of order 100 must be isomorphic to either of these four, because this is all the prime power decompositions of 100. But we know that there is a group Z modulo 100, which is an abelian group of order 100. So how do you settle this tension? I mean, I don't see Z modulo
Okay.
100.
So, okay. So that group has an element that is order 100, right?
Yes.
And none of these do.
Why?
Oh no, they do. The last one does, because 4 and 25 are co-prime.
Exactly.
Okay, yeah, it's that one.
Okay. So there is no mistake in the classification theorem. It's just another way of presenting it. Of course, the classification is only up to isomorphism. So, but this is the best you can hope for. I mean, saying what are the isomorphism types of all groups of a particular order. Okay, so this is a very powerful statement if you think of it, and we will see soon in the next part of the session a pretty strong result coming from the classification theorem. Are there any questions about what we did here? Okay, so I suggest we take a 10 minutes break and we come back for the second version of the classification theorem and some applications.
Great, thanks. See you in 10 minutes.
This call is now being recorded.
Okay, so let me pick up from this this last observation, which we talked about last time. This has a generalization for more than two factors. So, the proposition for positive integer with a prime decomposition let's say n is p1 to the n1 up to pk to the nk, you can write the group of integers modulo n as a direct sum of integers modulo p1 to the n1 direct sum integers modulo pk to the nk. And the proof is very easy. because once you can do it for two factors, you can just repeat it. So write let's say m is equal to p2 to the n2 times pk to the nk. Then I know that integers modulo n must be isomorphic to integers modulo p1 to the n1, direct sum integers modulo m, because of course p1 to the n1 and m are coprime. But then I just repeat the argument by trivial induction. I get integers modulo n being isomorphic to this sum. Okay. So this is easy, but it's a useful fact to record. And the next thing I want to talk about is a nice corollary of the classification theory. So as a corollary of the classification theory, we claim that finite abelian groups admit the converse of a Lagrange theorem. And what I mean by the converse of Lagrange theorem is, I mean, Lagrange tells you that if you have a subgroup of G, then the order of the subgroup must divide the order of G. The converse of Lagrange says that if you have any integer that divides the order of G, then you actually have a subgroup of this order. Now, we talked about Cauchy theorem. Cauchy tells you that if you have a prime that divides the order of G, then you know that you have a subgroup of this order, this prime order. But in fact, using the classification theorem, we can extend it for every divisor of the order of G. The way to go about it is, well, I mean, if you think of what the classification does for you, it decomposes G into a sum of cyclic groups. So whatever you want to prove, you first prove on cyclic groups, and then if it's true for cyclic groups, then you typically can extend it for any finite abelian group. So let's do the cyclic case. And let G be a cyclic group generated by lowercase g, a finite cyclic group. And suppose that n divides the order of G. So I can write n times k equal to the order of G. And since lowercase g is a generator, it means that the order of lowercase g is n times k. And if the order of g is n times k, I can look at the group generated by g to the power of k. This is the set of, well, E, which is gk to the 0, gk, up to gk to the n minus 1. Okay, when I do gk to the n, I get the unit element. I guess in our notation we don't use E, we use 0. But this is a subgroup. Is a subgroup of order n. Okay, so the converse of Lagrange theorem is true for cyclic groups. But then we can use the classification theorem. Yes, corollary, the better name. Let G be a finite abelian group, and n divides the order of G. Then there exists a subgroup H of G whose order is exactly n. Okay, so how do you prove this? Let's say M is the order of G, and I take the prime decomposition of M, say this is P1 to the alpha 1 up to Pk to the alpha k. Without loss of generality, I can simply write G equal, instead of isomorphic, to the sum of the primary P groups, or primary P subgroups. So GP1 sum GPK. And for each I less than equal to k, I know that the GPI is a direct sum cyclic groups of pi power order. So let's say z pi to the beta 1 sum integers modulo pi to the beta, and I put an index depending on I, so I call it Li. And of course, the sum of all the beta i's, let's say beta j equals 1 up to Li, it must be equal to alpha I. Okay. Now, since n divides m, which I remind you is p1 to the alpha 1 up to pk to the alpha k, we can write n as p1 to the gamma 1 up to pk to the gamma k, where the gamma i's are, of course, they must be smaller or equal than the alpha I, and they could possibly be 0. So it's bigger or equal to 0. Now, you can find delta 1 up to delta Li such that the sum of the, let's put it like this, delta 1 plus delta Li is equal to gamma I. And I also, and of course, so the delta j must be smaller or equal to beta j and possibly 0. Okay, so all I'm doing, I mean, this decomposition is not unique. I mean, the decomposition of gamma I into a sum of Li positive integers is not unique, but I don't care. I only need one such decomposition. And once I have it, of course, pi to the delta I, or sorry, pi to the delta j is going to divide pi to the beta j. But pi to the, I mean, here I have integers modulo pi to the beta j. And this is a cyclic group. And for cyclic groups, we know that, I mean, we know the converse of Lagrange theorem. So there exist H, let's call it like this, H I j, a subgroup of integers modulo p I to the beta j, whose order is exactly pi to the delta j. Okay, but then, so I have here, I have hi1. This is a subgroup of the first component. And I also have hi li, which is a subgroup of the last component. And I can take the direct sum of all these subgroups. Then hi1 direct sum hi li is a subgroup of well, of GPI, right? And the order of the subgroup, let's call it HI. The order of HI is the product of all orders. So this is pi to the delta 1 plus delta li. But the deltas were chosen to be such that their sum is gamma I. So this is HI is a subgroup of order pi to the gamma I. And remember, gamma, I mean, we started with an integer n dividing the order of the group G. We decomposed it into a product of prime powers, pi to the gamma I. And now we have found a subgroup of each of the GPIs of order exactly pi to the gamma I. So now we take the direct sum of all these groups, H1 plus HK. This is, of course, a subgroup of G. I mean, it's a subgroup of GP1 sum GPK, which is G by assumption. Let's call it age. The order of age is, of course, the product of all orders. So P1 to the gamma 1 up to Pk to the gamma k, which is simply the integer n. Okay, so this completes the proof. We found a subgroup of G of exactly order n. Any questions about this this proposition? Okay, so this shows you the power of this classification result. I mean, this is a much stronger result than what we had before. What we had before is only Cauchy theorem. And we can use the classification theorem, and the decomposition integers modulo n as a direct sum of integers modulo p1 to the n1 up to integers modulo pk to the nk, right? N is p1 to the n1 up to pk to the nk. To prove, well, to get another classification theory. And let me do this by example. So suppose I have G as a direct sum of integers modulo 2, integers modulo 4, integers modulo 3, integers modulo 9, integers modulo 81, integers modulo 25, and integers modulo 125. Now, we arrange all prime powers as the following. I put basically it's by order, but I put it in a table. So so 2 square, then 3 square, and 3 to the 4. This is 81. And then I have 5 square and 5 cube. Okay, and now I take each of these columns and I put it in one factor. So I can write G as integers modulo 3 plus integers modulo 2, integers modulo 3 square, integers modulo 5 square. And plus integers modulo 2 square. I guess instead of the prime powers, let me just write the numbers. So here I have 9 and 25. And here I have 4, 81, and 125. Now, observe that this guy, for example, is a direct sum of groups of order which is a pairwise coprime. So this guy is isomorphic to the integers of the product of all these guys. The product turns out to be 450. And same goes for this guy. It will be isomorphic to integers modulo the product. The product is 40,500. Now, the way I constructed the columns is that, the product of all the numbers in one column divides the product of all the numbers in the subsequent column, right? Because you have 3 dividing 3 square, for example. And the same is true for the second dividing the product of the third. So 3 divides 450, and 450 divides 4,500. Okay, so what we did here is we decomposed G into a product of cyclic groups, and the order of each of the cyclic group is dividing the order of the next one. And what I did in this example, it can always be done. It only depends on, I mean, the way I can arrange the table of prime powers. So this can always be done. This is the second version of classification. Theory in finite abelian groups. So let G a finite abelian group, then G is isomorphic to the sum of cyclic groups integers modulo n1 up to integers modulo nk, where ni divides ni plus 1 for each I between 1 and k minus 1. And the proof I leave for you as an exercise. This is really an exercise in kind of formal manipulation. I mean, what you need to do is, for a general prime decomposition or prime power decomposition, you need to figure out the way how to arrange all the prime powers in a table that will satisfy two properties. One is that the product of all numbers in one column divides the product of all numbers in the next column, and two, that all the numbers in one column, in a given column, are pairwise coprime. And once you did it, you do exactly what we have here. Okay, so this is basically what I wanted to say about finite abelian groups. Of course, the main example, and we will use it later on. An example. If E is an elliptic curve, which we haven't discussed, but I think you already saw the definition. Maybe actually in the first session I gave a definition. So if you look at an elliptic curve, and you look at the set of solutions, I mean, so E is, let's say, y squared equals x cubed plus ax plus b, with A and B elements of the prime field. In our notation so far, we called it ZP, but this is often denoted as FP. And now you can look at the set of solutions E over FP, which is all the elements x comma y in FP times FP, such that y squared is equal to x cubed plus ax plus b. And we will prove that this is an abelian group. Which, of course, it is finite, because it's the set of all pairs. Of a finite, a finite Cartesian product. So by the classification theorem, we have a lot of power. We know exactly what are the possibilities of a elliptic curve. The abelian group structure of the elliptic curve. So this will be very useful. And what's coming up next, and I think we will leave it into the next session, is finite fields. So the second ingredient before we get to elliptic curves is to do classification of finite fields. So of course there is FP, but there are other fields, other finite fields that are not FP, and it will again be important for us because you could look at the elliptic curve solutions over any finite field, and the classification of all finite fields will help us to organize this picture. Okay, so this is what is coming up next. Any questions, remarks?
So far, so good.
Okay, so I mean, I hope you got the feeling of what it means also to be rigorous. I mean, so far we did the classification of finite abelian groups with essentially all the details. I hope we can do the same for the classification of finite fields. And later on in these sessions, I mean, we will not be 100% rigorous. So it means we will introduce some black boxes, but I mean, quite not that often. So so this is what I mean when I say most of what we will do will be rigorous. It means with complete proofs. Okay, so if there are no further questions, I suggest we stop here.
Perfect. Just thank you so much for your time today.